Okay, it's time to look at the root port election. Now, what you have to understand is there's going to be a numeric value assigned to every interface in this topology. And what you're going to find is that numeric value is going to be inversely proportionate to the speed. So we'll say inversely proportionate. Now what that means is that the faster the speed, the lower the number. So what I'm going to do, just for the sake of clarity, is I'm going to assign every one of the links in my infrastructure a value of 1. So every link is going to allow me to be able to have a matching value that's assigned to it. Now the way this works is I'm going to, during this root port election, I am going to select the root port based on a principle called the lowest cost, where this numeric value is called the cost of the link. So as you can see, the faster the link, the more likely I want to use it, and I'm going to base this based on the lowest total cost because the cost is additive. As an example, from SW2, if I wanted to go to SW1, I see it's going to cost 1 point going out of this link. However, I have two other alternate paths. I could go from SW1 to SW3 at a cost of 1, and from SW3 to SW1 at a cost of 1, which is going to give me 1 plus 1, which equals 2. Another solution I could do is from SW2, I could go to SW4, so that's going to be a cost of 1. And then I could go from SW3 to SW1, which is going to be, again, a cost of 1 and 1. Or I can go from SW4 to SW1, which would basically give me a lower cost value, which again would be 2. Now, going straight across the link horizontally is going to be a cost of 1. So that's the link that I'm going to use. And based on this process, what I am going to do is I'm going to pick the interface that leads via the shortest path cost towards the root bridge. And that's going to be the interface that is going to become my root port. So what we see here is these interfaces all would become root ports. Now, root ports lead towards the root bridge. It's also going to be important for us to understand that we also have another port type called a designated port. Designated ports lead away from the root bridge. So looking at it purely from the perspective of the root bridge itself, what we're going to see here is these interfaces, since every interface leads away from the root bridge, would be a designated port, DSG. So that's a designated port that leads away from the root bridge. Now what we see here is the beginning of the creation of what I call the loop-free computational graph. So if I look at this and I look at this graph, the important thing for us to keep in mind is this graph is going to allow me to be able to build a tree. That's why we call this spanning tree protocol. It is a protocol that is going to allow me to build a loop-free graph or tree whereby branches of the tree do not intersect, therefore I prevent loops, and it spans multiple switches. So in this scenario, what we're going to find is at the top of this loop-free graph, I'm going to have SW1 because it was elected my root bridge. Then what I'm going to do is in this scenario, I'm going to have 3 devices that are going to be connected via the ports that lead towards the root bridge, and these are going to be my root ports. Now at the end of the day, if I had a bigger topology, I may have interfaces that are leading away, but we can see here I have switch 1, switch 2, switch 3, and switch 4. So you see here I have a computational graph whereby SW1 is the center of the layer 2 fabric, and as such it has paths that are going to lead to each of these individual switches in such a way that I'm not going to have loops in my topology. Now, the key element here is if I were to lose a link, let's say this link right here goes dead, that means SW4 would no longer be connected to SW1. Well, the benefit here is what would end up happening is SW4 would now have the ability to be able to pick one of these 2 links to go active. So what will end up happening is that it will actually remap itself. This is called reconvergence. So we see here we have a self-healing infrastructure that's going to allow me to be able to recover in the event of a link failure, and at the same time prevent the possibility of generating loops through the creation of this computational graph that I just walked us through. And the main goal of this entire exercise is to have an efficient mechanism with regard to being able to send data at layer 2 while protecting ourselves from the fact that our frames do not have TTL values, unlike packets. Packets do have TTLs. So we've elected the root ports, we've elected the root bridge. Now what we need to do is we need to take a look at what's happening in the rest of the topology, and what we're going to find here is that any interface that is not being used to reach the root, well, that's not the one I wanted to use. Any interface that's not being used to reach the root bridge via the least cost path is actually going to be blocking. So if I go through here, this interface is blocking, this interface is blocking, and this interface is blocking. Now, there is, like I said, a problem with this, and that is the fact that spanning tree helps me, but it comes at a cost. And that's what we're going to entertain in the next video, where we take a look at how spanning tree saves us one way, but harms us another. I'm Terry Vinson, and I'd like to thank you for learning Data Center with me.